relational algorithms from the perspective of the algorithms community. Truth is, I did not really realize the full potential or benefit of this program until Kirk and I started basically trying to organize this relational algorithms day, and we started realizing the disconnect in terminology. So hopefully we will be able to talk the same language and understand each other better after this program.
Yeah. So there's two. A couple things here. One is I want to go sort of give my take on the some of the things Mahmoud did, and then I want to talk about some additional algorithm design technology. So just recall, relational algorithms are algorithms that are efficient if the input's in relational form. So just as an analogy, you can imagine trying to search for a string in a compressed text. Okay, so one way to do that is uncompress the text and then do your standard search algorithm. But the problem then is you have to pay the cost of uncompressing the text. Okay. So there's algorithms in the literature about searching directly on compressed strings without having to do decompression. And that's sort of analogous to the same thing here. Like when the data is stored in relational tables, the data is compressed, and you'd like to avoid the cost of decompressing it. So what are the takeaway points that I want to get across, particularly to the algorithms people? This is an interesting algorithmic area that's not received much attention. And since my PhD student who's working in this area left, I've sort of paused, and it'd be great if somebody else wanted to work on this with me. There's presumably lots of interesting open problems, but if you're going to work in this area, you have to put some work into finding the open problems. So you need to sort of it's not like fruit picking, it's like mining. Sort of this relational algorithms model is a kindred spirit to other restricted computational models, for example, like the MPC model or the streaming model, where what the algorithm can do is more restrictive than, say, your standard RAM model. So a lot of the times the secret to success in these areas is being able to find problems that you can solve in these restricted models. Like if you just take your average problem out of CLRS and try to solve it in these models, it's just too complicated. You need to look at simpler problems. All right. So here's, if you're an algorithms person and wanted to get started in this area, here's the things I think you need to know to get started. I'm just going to go through these. So first you have to know what a join is. So, there's a couple ways about thinking about a join is. One is you can sort of think about, if you're joining two tables, you can kind of think about them as bipartite graphs, two different bipartite graphs, and the variables that you're joining it on, you sort of identify those two. So then what you're doing in the join is these two hot paths that you get. All right. Another way of thinking about what a join is, and the way that I sort of like, is geometrically. So you can think about the join as points in some higher dimensional space. Okay. And what happens, if I take the join of AXY and BYZ and then project back to XY, well, I get exactly my original table AXY. Okay. And if I join AXY with BXY and project down to the plane YZ, I get back to my original table BYZ. Okay. So one way to think about this these are points that are stored by their projections into lower dimensional spaces.
But this is actually not always true, because in A you might have dangling tuples that do not join with B. So after you do the join and project, we might get pure tuples.
Okay. All right. So again, this is sort of a way to think about what's going on. There's some things I'm going to say that are oversimplifications. But that's sort of the way that I like to think about these things. All right. Good. So, here's sort of a table of, some of the research in this area, and you have sitting on top some problems which relational algorithms have been developed for. In the red, or you find some algorithmic techniques. But the key point to take away here is that everything rests on these sum product queries. Every algorithm we know at the base is somehow using sum product queries. Okay. So we, in some sense, we don't know how to do anything that's not based on a sum product query. So let me go back and review sum product queries. And the first thing I'm going to do is just change Mahmoud's definition of what a sum product query is. I'm going to throw away the tables. Okay, I'm going to abstract out the tables. Okay. So for me, a sum product query is you're taking a sum over the rows of the join, and then you're taking a product over the columns of some function of that entry. Okay. So for example, okay, so like, what are problems you sort of take this geometric view of what the join is? So it's points in higher dimensional space. So like, what are problems you might try to develop algorithms for? Any geometric problem where the input's a collection of points. All right. So for example, one geometric problem is how many points are in the input, right? You would not find that in any geometric algorithms book. Why? Because it's too simple, right? I mean, you wouldn't even teach that in the CS1 course. But if the points are in compact representation, that is interesting. What point is farthest from the origin? K-means, for example. Those are all, problems where the input is points. So, all right. So let's consider the problem of how many points are in the input. Okay. If you have an explicit listing, this is trivial. If the input's in relational form, it's just NP hard to decide whether the list of points is empty or not. Okay. It's sharp P hard to count the number of points in the input, right? So that would seem to be a negative result. But at the end of the day, we don't really care, right? We want to sort of do our algorithms in terms of sum product queries. And if the structure of the table is very complicated, that's somehow that's not the fault of our sum product or our algorithm, our relational algorithm. That's the fault of whoever designed the tables. Yes?
Which form is NP have to decide if the input is not empty? What would be the form?
If the tables are relations and you want to know whether the join of the tables is not empty.
Any arbitrary number of joins.
Yes. So, okay, good. So how can I write this as a sum product query? Well, I just sum up over the rows of the product over the columns of 1 for each column. Right? This is sort of a trivial sum product query. So, for this table over here, I'd have 8 summands. Each of them is 1 times 1 times 1 because there's 3 columns. All right. So now that I have that, I can now feed it to the, the variable elimination algorithm that sort of sits beneath that, but I don't need to worry about that. Once I have a sum product query, like that'll be the base of my algorithm. All right. How about if you want to know the furthest point from the origin, say in the 2 norm squared? Well, okay, so then this is again the tropical semi-ring that you saw in Mahmoud's talk. I take the max over every row of the sum of the squares of the columns. Okay, so for this particular table, it'd be the max of 3 squared plus 1 squared plus 7 squared, or 3 squared plus 1 squared plus 8 squared, and I take the max over all of those, and that'll give me the answer. All right, so that's a sum product query, and that sort of can be that I can do that as a base operation of my algorithm. All right, so now I want to give some examples of using sum product queries to develop algorithms. All right, and I'm going to use as a running example k-means clustering. It's the classic algorithmic problem. So the input for this problem consists of a bunch of points and an integer k. And what I want to do is then I want to find k points that in some sense represent the x's well, that are summarize them well in some sense. So I want to find 3 points, these 3 red points here, S1, S2, S3. such that if I look at the distances from all the blue points to their nearest red point, that's minimized. So the aggregate distance, okay? And I'm going to use the 2 norm squared distance, so the normal distance squared. All right, good. So now when we're designing relational algorithms, you know, we sort of develop the following strategy. There's a plan A and a plan B and a plan C. So plan A is if there's already an algorithm out there, that's the algorithm, right? That's the standard algorithm. Can you relate that, implement that algorithm in a relational way? So what does it mean to implement in a relational way? You could produce the same output that that algorithm does, but maybe you compute it differently. Okay, but the output is the same as the standard algorithm. Plan B is, you know, okay, I can't implement that algorithm, but I'm going to implement another algorithm that gets whatever the guarantee is that the original algorithm got. So if the original algorithm was, you know, 4 approximate or something, I will try to design another algorithm that's also 4 approximate or maybe 5 approximate or something. But it sort of has the same guarantee. So if you were happy with the standard algorithm, you should be happy with this one. And then plan C, that didn't work. You know, well, what can you do? Can we do something? Can we do something weaker? All right. So what are some of the k-means algorithms? So one k-means algorithm is k-means plus plus, which is the most cited paper to ever appear in SOTA, apparently. But what this says is you pick the next center with probably proportional to its distance to the nearest previously picked center, right? So if you have some point that's very far from all the previous centers, probably you're likely to pick that one, or you're more likely to pick that one. And one thing we discussed over beer last night was that one cultural difference between the database guys and the algorithms guys is we don't put randomized algorithms. Randomized algorithms are real algorithm to us. So I didn't even bother to put randomized algorithms. All right. So, you know, another algorithm in the literature is this adaptive k-means algorithm. And, you know, if you try, you can prove that if you, you know, to be able to implement this algorithm, to be able to compute the same output that this algorithm does, even if the tables are very simple, is NP-hard, right? So it's not reasonable to expect that you can implement exactly this algorithm. So then what did we do? We had to go to plan B. Plan B was, okay, I'm not going to compute exactly the same weights that this algorithm does. I'm going to compute alternate weights, but those alternate weights give me the same theoretical guarantee as the original weights.
Can you explain what the sentence in plan A means? How would this imply? What is the technical result behind this?
Okay, so a problem is, you know, NP-hard if you have a polynomial time algorithm for it, you know, if you give a polynomial time. So, you know, the input to this problem would be your relational representation of points in high dimensional space. And the output would be the weights that this other algorithm produces, right? So if you know, if you're able to produce those weights, then we're able to, you know, somehow we're able to reduce satisfiability to producing those weights. So if I knew what those weights were, then I could decide whether a formula is satisfiable.
Sure, but I understand that. But the non-relation implementation, how does it avoid this pitfall, the non-relation?
Because it's doing, so it has an explicit listing of the points.
Okay, so it's the implicit representation again.
Yeah, so everything, the hardness comes from the fact that there's this compact representation. And sometimes, so first off, if the compact representation is very complicated, there's nothing you can do, right? If you just want to know whether the join's empty or not, that's NP-hard, right? So our usual assumption when we start is that, you know, the tables aren't complicated. But even if the tables aren't complicated, it still could be complicated to compute some things on them.
So what does it mean for this NP-hardness result? Is NP-hard for non-complicated tables?
Yeah, so we have, I don't remember exactly, but it could be, for example, that the tables are just a cross product join. I don't remember exactly what the structure is, but there's some structure of the tables that you look at them and say, okay, those are not. You know, you can't say that the structure of the table is complicated. Like if you look at the structure of the table where the proofed NP hardness decide whether the joint is empty or not, those tables clearly encode a SAT instance. All right. Good. Oops, I messed this up again. It does not like when it goes off. All right. So, so there's, okay, so now there's sort of plan A, B, and C. You know, once you decide what you're going for, there's sort of, I kind of broke, you know, maybe I'm trying to find a relational algorithm that has the same approximation guarantee as the standard algorithm. There's sort of 3 different levels of approaches. First, if you can just write the problem as a sum product query, you're done, right? The second is to sort of try to design something from scratch. So you're trying to, you know, like it's not obviously a sum product query, but maybe I can, in some non-obvious way, write it as a sum product query. And then our strategy is, instead of trying to do it for arbitrary, you know, sort of in arbitrary query, we sort of have a warm-up. First, we try a cross product join, and then we try a path join, and then we try to generalize it. And then C is you just, you know, it's a standard thing. You've already built up a bunch of things you know how to do with some product queries, and you just, you know, try to use those. All right, so let's talk about one means plus plus. So one means plus plus just means you want to pick a point uniformly at random from the input points. So one thing you can do is sort of reduce uniform generation to counting. If you can count, then you can uniformly generate things. So if you look at, so this is our sum product query at the bottom that counts. Okay, so if you go look at the implementation of that, what the variable elimination scheme will give you at the end. So, all right, so let me back up a little bit. So let's think about this on a path query. Okay, so a path query means that I'm joining together tables with 2 attributes per table, and you know that the second attribute of one table is equal to the first attribute of the next table. So if I join these 4 tables together, this is like I have a layered graph with 5 layers. So you know, what would the counting problem here would be to count how many paths I have from the first layer to the last layer. Okay. If you do that, you know, what this variable elimination algorithm will end up with at the end is you'll end up with a count for each, you know, each of this vertex at the end. How many paths do I have ending up there, right? So, you know, the number of paths I have ending up where feature or attribute 5 is 1, is there's 4 of them, right? So now if I have these numbers 4, 4, and 1, I can do uniform generation, right? I pick with probably 4 9ths. I pick a point where the 5th attribute of the 5th feature is 1, and I just go backwards and do that. Okay. All right. So so you know the implementation of one means plus plus is just the sum product, you know, sort of the reduction from uniform generation to counting, and then using a sum product query. All right, the second one is 2 means plus plus.
Can I ask a question?
Sure, go for it.
So why is it trivial once you count to sample? Because you want to sample from your relational instance, right? You don't have the explicit representation.
Yes, but I know if I joined it together, right, there would be 9 rows in the join.
Yes.
Right? And 4 of them would end up with feature attribute 5 is equal to 1. Right? So if I picked, conceptually, I pick one of the rows that has 1 is the 5th attribute with probably 4 9ths, I haven't made a mistake, right? I'm doing toward uniform sampling, right? And then you sort of have to trace this back. I mean, this is like for I mean, I think of all this in terms of shortest path, right? So like, if you want to find the shortest path, you just sort of trace it back. Where did I come from? And it's that's
But
sort
then
of how it
you
works.
would have to have all the intermediate counts.
Yes. Yes. All right, good. All right, so now I want to do two norms plus plus, and I want to pick a point with probably proportional to its two norm distance from the previously picked point. Okay, so now I'm going to again want to reduce uniform or random sampling to counting. So what I need to do is I need to count the aggregate two norm squared of the points. So again, here, if I do the same thing, if I look at the sum of the two norm squared for all the points in the join where the fifth attribute is 1, I'll get 32 if I haven't done the math right. Okay, so then I can, pick out a point where the fifth attribute is 1 with probably 32 over 32 plus 44 plus 45 and do the same trick. All right. Good. All right, so how am I going to compute the two norms squared? Okay, so as a warm-up, let's look at a path query. Okay, so again, I want to compute the sum of the squares of the attributes on the path. So let's just think about an edge here going from y to z. Right, and I'm extending my sum when I'm at y to z, right? So what is my sum of the squares at z going to be? Well, it's all the sum of the squares up to y, plus there's going to be some y squared terms I have to add to it. Well, how many y squared terms I'm going to have to add? I'm going to have to add the number of y squared terms as the number of paths that end at y. Right? And then the number of paths that go to z is the number of paths that go to y. Number of paths that go to z plus number of paths that go to y. Previously went to z. All right, so what does that suggest is the two things that I need to know are the sum of the squares and number of paths. Like this is like an undergraduate algorithm. So now, how do I go to a sum product query? So the two things I'm going to need to know: what are the elements of the base set of my semi-ring? There's going to be pairs. Okay, one's going to count the number of paths, and one's going to be the sum of the squares. Okay. And now, when I do a variable elimination algorithm, think about trying to eliminate this variable y here. Right? So for the moment, think about doing shortest path. Right? You want to compute the shortest path to z. Right? And this is, given this information here, well, it's either the shortest path you had to z before, or that's the shortest path to a plus y squared. Like that's the standard relax operation in all of the Dijkstra, Bellman-Ford, or whatever. So we want to do the same thing here, where min is the semi-ring sum, and addition is the semi-ring product. Right. So I've just rewritten up on this line as I just change min to plus and the semi-ring plus and addition to semi-ring multiplication, and then you want to get this is my new answer. Okay, this is the number of paths should sum, and then the sum of the squares should I have to add NA copies of y squared. Okay. So my goal is then I need to design a semi-ring plus and a semi-ring product so that this gives me the answer that I want. All right. So then if you play around this for a while, turns out that this is the right thing to do. Okay. In the semi-ring addition, I want to add both components. I want to add the sums and I want to add the numbers. And in the product, I take the product of the first coordinate and somehow something like the cross product of the second coordinate or something like that. Okay. And with that, multiplicative at ending 1, 0 and the additive 0, 0. And if you go plug that in, it does what you want. It gives you the right answer. Okay, but I designed this semi-ring from sort of looking at this, looking at it in the pathway of looking at it. All right. So I found this interesting when I was doing this, is that some product queries you can sort of solve with dynamic programming. So for example, shortest path is a sum product query, and Bellman-Ford's a dynamic programming algorithm that solves shortest path. Turns around that the other is true as well. Like I can implement some dynamic programs as a sum product query, which I did not know beforehand. And kind of roughly speaking, what is the base of the semi-ring? The base of the semi-ring is like a row in your dynamic program. Okay, so then when you're sort of doing these sums and the products, you are combining these rows in dynamic programs, so that when you're done, in some senses, conceptually, it'd be the answer that your dynamic program got. Okay, I'm not going to be able to get into this. This is sort of in too much detail, but I just wanted to sort of point this out because this is somehow a step toward dynamic programming. So now the base of my semi-ring is structured data here. All right. All right. So now on to three means plus plus. So now I want to select my third center with distance proportional to its distance to the nearest of the two previous centers. Okay. So if, say I pick this S1 and this S2 are my two previous centers, if I look at the separating line, I want to pick the green points that are to the lower left of the separating line with probability proportional to their distance to S1. And I want to pick the points up and to the right of the separating line, probability proportional to their distance to S2. So now, how did we do this? For the last example, we sort of reduced this to summing up these distances. Now, it turns out that this is, we can construct, this is NP hard. We can construct sort of simple tables, simple instances where if I can compute the aggregate distances to the line from these points, that would give you an algorithm for your favorite NP hard problem. So therefore, we can't do this trick that we did last time of reducing random generation to summing. That's not going to work. All right, so we need a plan B. And the idea is to use rejection sampling. Okay. So the idea of rejection sampling is you can use, you have there's a hard distribution you'd like to sample from, but you can't do that. So what you do is you try to find an easy distribution that in some sense is close to the hard distribution, and then try to sample from that. Okay, so this is the standard example. Maybe you want to uniformly sample from the blue circle. Circles are kind of complicated. Maybe that's hard. So what you could do is uniformly sample from the red square. And then if it's outside of the circle, you can decide whether points in or outside the circle. Then you could reject the points that are outside the circle. Right? That would end up giving you a uniform sample from the blue circle. And if the area of the blue circle and the area of the red square are relatively close, you shouldn't need too many samples until you get something from the blue circle. It should be relatively efficient.
Kirk, can you go back a slide?
Sure.
Okay, so I had been trying to think about this as just like, okay, I can just think about dynamic programming as, my branching step is, I can branch if I have, like the right additive structure for the semi-ring, and then within each subpiece, I just need to find the right like multiplicative structure for the semi-ring. But what you're actually saying here is that isn't everything, because it can be NP hard to do, like when I'm looking at the compact representation, it's NP hard sometimes to do that branching step.
So I don't know what that branching step is. I mean,
like my recursive step in my dynamic program.
So I don't know what dynamic program you're talking about here. I mean, this is just your standard, NP completeness proof or whatever. You have to.
Okay, so it has nothing to do with.
So I mean, there's no algorithm here. I mean, I just show that your favorite problem is NP complete. You show how to take your favorite NP complete problem, construct an instance of this where the answer would tell you, the answer to your favorite NP complete problem.
Okay.
Maybe in retrospect, maybe I should have put one of these reductions up here, but they're really just, if you know how to do NP completeness proofs, you can do this.
Yeah, there's nothing else going on. Okay.
All right. Good. So how do we do this? So what's, all right, so this is just more rejection sampling. So, conceptually, we, take the space and divide it into sort of 3 parts. One is we put a box around S2. One is we put an axis parallel box around S1, and then there's the points that are outside of either box. Okay. And I guess the key fact is the points that are outside of either box are roughly equally close to either center. The points that are very close to one of the 2 centers are in the box. Okay. So then what is our distribution that we sample from? If the point is in box B2, we use the distance to S2. And if it's outside of box B2, we use the distance to S1. Okay. Now, so now, so now what can go wrong, if we end up sampling a point that's sort of on the left, if we end up sampling a point that's up and to the right of the purple, but outside of box 2, we got the distance wrong, right? Because we used the distance to B1 and we didn't use the distance to B2. Okay, but those are close, right? So, okay, we just reject it with some probability, that has to do with the ratio of the distance from to S1 and S2, and we just try again. But that's because they're close, that'll only happen half the time or something. All right. Good. So if we look at your sum product query, so these are these individual skip that. All right. So the conclusion is, even though it's NP hard to do the sum, we can use rejection sampling because we can find a distribution we can sample from using sum product queries that's close. All right. Let's see what's the next one. All right, so the next one that we wanted to talk about is counting the number of points in a hypersphere. Where did I go? There we go here. All right. So this is to do this. This is an example of the thing that Mahmoud mentioned at the end, which is a sum product query with a constraint, right? So what do I want to do? I want to count all the points in the hypersphere so that my sum product query is just my standard counting query, count the points. But now I only want the points in the hypersphere, right? So I have a constraint here. I should only accept those points that lie in the hypersphere. Okay. All right, so in general, solving some product queries, even with a single constraint, is NP hard. But a lot of times we can approximately solve the sum product query within a factor of 1 plus epsilon, as long as our semi-ring has, some structure that the operations are approximation preserving, okay? Which mostly means not subtraction, okay? So you just need, if I approximate these two things and apply the operation to them, the result will be an approximation of the exact, product and then approximating, which is not true of subtraction, but it's true of all the other standard operations that we've seen today. All right. So, as a special case, I can count the points in the hypersphere centered at the origin using this sum product query with an additive inequality. Okay. And the algorithm for doing this is, again, implementing a dynamic program, which I didn't want to go into.
So, sort of you're saying additive inequality because the thing on the left is in sum, or?
I mean, it looks like a linear inequality, but the things you're adding up don't have to be linear. So here, I'm summing up the squares of the entries. All right. So again, just the takeaway points. This is potentially an interesting area if you're willing to put in some more, but the initial start is we have to find some problems. What are some, if you're sort of interested in this and you want to come back at 2, what are some things that you might discuss? Well, one thing is just what would be some interesting geometric problems to think about, right? Something that's easier than your normal geometric problems that might be interesting to develop a relational algorithm for. And then we also have like a homework problem. So when I onboard people into research, particularly students, rather than have them read papers, I like to give them homework problems so they can discover the basics themselves. So we have Mahmoud and I came up with a homework problem, which is implement the standard ID3 decision tree algorithm. So I'm going to just tell you a little bit about that now so that we can hit the ground running when we get here at 2. So, imagine that I have my table. This is a supervised learning problem. So I have a table, and one of the columns is a label which tells me whether this is a positive or a negative instance. Okay. And I'm trying to build a decision tree to help me do classification, but I don't really need to do this here. Understand this here. So I can think of my table having an entropy. So it's the standard binary entropy function on the fraction of table entries that have a 0 label and the fraction of entropes that have a 1 label, right? So that's a binary variable. It has an entropy. Okay. So here, a third of the tables, a third of the entries are 0. So the binary entropy would be 1/3 times log 3 plus 2/3 times log 3/2. Right. So the core of the ID3 algorithm is to find a comparison that gives you the most information. Okay, if I about whatever the about the label of what I'm asking a question about, or equivalently that the resulting conditional entropy be minimized, right? If the resulting conditional entropy went to 0, then I've completely learned what I need to learn. So, for example, if I have this table, one possible comparison is u less than 4, right? So so that would sort of maybe be the root of my decision tree. So now what would be the resulting conditional entropy of u less than 4? Well, 2/3 of the entries are less than 4, so it'd be 2/3 of the entropy of the entries that are where u is less than 4 plus 1/3 of the entropy of the entries where u is greater than 4. So, for example, the conditional entropy when u is less than 4, I have 3 entries that are 1 and 1 entry 0. So it'd be 1/4 log 4 plus 3/4 log 4/3, right? So the algorithmic problem is find that comparison, right? That gives me that minimizes this conditional entropy. All right. And there's multiple. It's sort of a good warm-up problem because there's a base obvious algorithm that just uses some product queries, and then you sort of think about this. There's a slightly more efficient algorithm that requires a slightly more sophisticated understanding of some product queries. But this is a good warm-up problem. So this will be one option for this afternoon. All right. So I guess I went through that a little quicker than I thought. So, but I don't think anybody will object going to lunch early. Any questions?
Specifically, any questions about the homework problem? O'clock session.
Can you go for it?
So I have a question about the k-means are the
Yep.
the path. So that basically you encode it as a sum product, right? So then it shouldn't matter if it's a path as long as you have a cyclicity, then you get.
So I can just write it as a sum product query, whether the table is very cyclic or not. The way I view the world is not my problem.
Okay.
That's database guy's problem.
The path was just an example, right? So basically what you can actually, what's happening is that you can use the sum product query over your tables, and then whatever structure the relation table have, that will affect the sum product query.
Yeah. So my advice to the algorithms guys and maybe the database guys is solve the problem on the path query, because we like graph algorithms, right? We teach graph algorithms for 20 years. I'm happy with graph algorithms. Solve the graph problem. Once you understand that, usually it just maps over to some product query relatively simply.
Okay. So from the path, you get the intuition of what is the right semi, and then that gives you the sum product query, and then.
Yeah, I mean, so for the example with the sum of the squares, I realized on the graph, this is the basic algorithms homework problem. Count the sum of the squares of the link, the links. I know how to do this. I need generalized recursion to keep track of both the number of paths and the sum of the squares, and then I can design. Once I know that that's what I need to keep track of, then I can design my semi-ring.
Yeah, so that's apparently one gap in communication between the database versus the algorithms people, is that apparently the algorithms people prefer to use shortest path as the origin of everything and measure everything in terms of it. So welcome to the last 3 years of my life.
Yeah, he's always saying, oh, it's matrix multiplication. I'm always saying, oh, no, it's shortest path. So.
Kirk, do you want to tell everyone the exact time you have for the afternoon?
Okay, good. So the plan for the afternoon is we're going to show up at 2. Nofer is going to put 2 of her problems up here. I'm going to put relational algorithms up here. So there'll be 3 things. I'm going to split you into the 3. You pick. Go stand by the problem you're interested in. And then we will split those groups up. So there's 15 people over here who want to work on Nofer's 12-cycle problem. Then we'll split those 15 people up into 3 groups of 5, where they're not all database people or not all algorithms people. Go talk. Give us feedback how it worked today, and then we'll decide tomorrow. If you're much happier with open problems and you hated this, and we'll do that tomorrow. If you love this, we might do it again tomorrow. It's sort of a day-to-day thing.
Yeah, so we'll split people into clusters using k-means.
All right, enjoy your lunch.